Centroids. Centroids. We were talking about centroids like the first moment of area, first moment of an area, because the centroid is based on, let's see, we're talking about something like f bar equals to integral of x dA over integral of dA, or which is the same x dA over area, right? I want you guys to be aware of the fact that the centroid, this is like the geometric center of a figure, and it's based on the fact of the point where the weight of something is located. That's the point where the force of the earth is applied to the object. That's kind of like the basis of the centroid. When we talk about centroid of areas, the areas don't weight, the areas don't have a weight, but the basis of the centroid of an area is the earth pulling down towards an object. So as we said, an object is made of many particles. Each particle has its own weight. So the air is pulling down every single component of the object. Those delta W that we mentioned the other day. And if we do the summation of all the particles, the particles that compose the body, you have the total weight. And if you want to work on a real analysis of a problem of equilibrium, you cannot work with the delta W because they are too many to deal with, too many weights to deal with. So you have to you usually work with just the total weight of the body, and you locate that weight somewhere in a specific somewhere that is called the center of gravity. And the idea is to find the location of the center of gravity in such a way that the effect of all the weights, all the little weights, the effect of all of them is equal to the effect of the total weight. So you have to put that total weight in a specific location in such a way that the effect of the total weight is the same effect as the effect of all the little pieces together. And the way we do that is by making sure that the total weight is equal to the summation of all the little weights. And that the moment that the total weight produces with respect to some point, let's call it A, is the same as the moment produced by all components together. And that's how we calculate the location of the center of gravity. That's the basis of the centroid or the center of gravity. The summation of all the weights has to be equal to the total weight, which is kind of like a common sense thing. And that the moment produced by this weight the location is such that the moment produced by the whole weight is the same as the moment produced by all the pieces together. That's how we calculate that. So if you have a point here, let's call it A. Actually, we were using the origin of coordinates, X and Y. So the moment produced with respect to the origin of coordinates of all the little weights, well, it's equal to all the distance of all the little, let's call it xi, the moment of all the little will be the summation of x times dw. That's the moment produced by all the little pieces. Has to be equal to the moment produced by the weight, that will be the total weight here, multiplied by this distance that is called x bar. So it's equal to x bar times w. And then we went into that, if we were talking about thin plates, we calculate the weight as the specific gravity times the volume of the plate, and the volume of the plate is the area times the thickness of the plate. And then we cancel out the specific gravity and the thickness. We cancel those in both sides of the equation, and that's how we end up with x bar times area equals to summation of x times dA. And we end up with x bar equals the summation of x dA. Actually, we were talking about delta W. When you use summation, it's kind of like a finite number of elements. And then if you are talking about a continuous summation of all the infinitely small components of a body, we don't talk anymore about delta, but we move to the calculus expression of D. So we have x bar equals to integral of x dA over A. Or you can express the A as integral of dA. And that's how you find the center of gravity of an area. And we did that when you know the location, when you can find that your body is component, the components are a finite number of elements. You do the little table. Remember the little table we did the other day, where you put here the number 1, 2, 3, the a sub I, x bar sub I, y bar sub I, and then ai, xi, ai, yi, and you do the summation, here, here, and here, and then that's how you get x bar as summation of fi x bar I over summation of ai, and same thing for yi. And we did an example, or two last class, okay? And we need a couple of examples of finding the center of gravity of a couple of figures. I guess we did the center of gravity of a rectangle, the center of gravity of a triangle. Maybe we should do one more example of those. And once you have the location of the center of gravity of a few basic figures, then you can use those basic figures to find the center of gravity of some other more complex figures made of those simple figures from which you already know the center of gravity. Or you can find those center of gravities on a table. Your book has a table in the last page. I think I have that table here. Let me see if I can show it to you. Yeah, this is the table from the book. And you see the centroid of some areas. I see very little. I don't know if you can see it. For example, I think we found, well, these are not the ones that we found the other. The centroid, have centroid location of a sector of a circle, a quarter of a circle, half a circle, a trapezoid. I think we did the section of a parabola. Okay, and you can find tables with more simple figures on the books or on your internet. So you can use those in order to do the table for a more complex figure. Maybe and now you can do this table for any figure that you have. It's kind of like the easiest way and the more organized way to do. But not necessarily. Let's say we do a very simple example here. We did an example the other day with a figure that was based on triangles and circles and rectangles. But I want to know if you guys would be able to do something like this. What is the center of gravity of a figure like this? Let me draw something like here. X. Let's do only X bar. Let's see that we have a circle here with radius equals to 1. Then let's see, let's do radius equals to 2. And then we have here a square that is 3 by 3, and another little circle here with radius equals to 1. And this one is located here at 6, let's say this is inches, so this is that 6 inches, 2 inches, 3 inches, 1 inch. And this one has the center of gravity here as 18 inches. And this one, a center of gravity here, 25 inches. And I can think about the center of gravity of, let's say this is a composed figure that is maybe connected by a link here that has a neglectable area here. So where is the center of gravity of this figure? What is X bar? So that will be then we could do the table that we did last time, or we can go directly like X bar equals to summation of area times distance. X bar equals summation of xi times ai over total area, right? So we can do here, the first one is, the first area is pi 2 square times the distance, 6 inches, plus the second one is 3 by 3 multiplied by the distance, 18 inches, plus the other one, which is pi 1 square times 25 inches, divided by pi 2 square plus 3 by 3 plus pi times 1 square. And that's the center of gravity. Or we can do the same table that we did last time. This is area 1, this is area 2, this is area 3. So you do number, L sub I. I'm gonna do only X bar, not X and Y, just X bar. A sub I, X bar sub I. Area 1, area 2, area 3. Area 1 is R2 square. Area 2 is 3 by 3. Area 3 is pi 1 square. X1 is 6 inches. X2 is 18 inches. A3 is 25 inches. So if someone can have, oh, this is pi right here, pi. Okay, what if somebody helps me here with pi times 4?
12.57.
12.57.
Yeah.
3 times 3 is 9. And this is 5. 3.14. And then we have 12.57 times 6. Times 6.
75.4.
4. And 9.18.
162.
62. And 3.14 times 25.
78.5.
78.5. So now we do the summation here. 12.57 plus 9 plus 314.
24.71. The first one.
21. And this one right here. We don't need this one.
315.9.
Yes, okay. So then X bar equals to summation of Fi xi over summation of ai equals to 315.9 over 2471.
12.8.
12.8 inches. Put 12.8, so meaning that 12, so this is 12, 6, 12, that will be something like over here. This is the center of gravity of our figure. Everybody happy? All right. Any question? This is kind of straightforward. You should be able to do this, or for a figure. Eventually, you might need to calculate something like a beam like this for a specific application or any other figure. Let's do one last problem now with the integral, and we can finish with this topic. You just do your homework. One last example with the integral will be, let's try to calculate the center of gravity of, this is too little here, of a basic figure like as a quarter of a circle. The center of gravity will be somewhere over here. We don't know where, but we need to find this distance, x bar. In order to do the center of gravity of a basic figure by integration, I mean, the idea is that you have to find first a differential of area from which you already know the center of gravity. The examples that we did last time use differential of area that were rectangles. That we have something like this shape, where you know the location of the center of gravity of this because we already find them. We know the center of gravity of a strip, and also we know the center of gravity of a rectangle. We did it last time. It's right in the middle, and it's also like common sense. We found the center of gravity of a couple of triangles, this triangle, and we found that if this is H or this is H, the center of gravity is at H over 3, or if you measure from the top, is 2H over 3 by subtracting the total height. So if you have a shape like this, then you can find figures that are made based on those basic figures. That should be the case here. We can do a differential of area that has this shape here, where this is a very little angle, or this angle, if you want to call it here, d theta, right? And this is a triangle because being this so little, this doesn't look like an arc. It's just, it can be considered a straight line. So that would be the base of the triangle, and the radius will be the height of the triangle, this distance here. So we know that the center of gravity of that little area that I'm shading here in red now, the center of gravity is at two-thirds of the radius. So this distance from here to here is 2/3 of the radius. So if we want to find x bar, let me put it down here, x bar, which is the location from the centroid of the figure here, x bar. We are going to do this equation, x bar equals to integral of x dA divided by integral of dA, right? Where integral of dA is just the area that we know it here. The area of this is just 1/4 of dr squared, right? We don't need to do that integral. But we can do it by integral also, as someone mentioned last time. This is just calculus 101. So let's do this. We are going to do the numerator of this, which is the integral of x dA, where dA, we need to specify dA very clearly. dA is equal to 1/2 dh. So 1/2. The base is this distance here, which is r times d theta, right? By the definition of radians, and that angle will be measured in radians. This is from the definition of radians. So will be r d theta multiplied by the height of the triangle, which is from here to here. This is the total height. So that total height will be the radius, right? That's dA. So that's dA. And what is x? X is the distance from the origin here to the center of gravity of that differential of area, which is 2/3 of the radius multiplied by cosine of theta, where theta is this angle here. So x will be, let's put it here, 2 integral of 2/3 of r cosine theta multiplied by dA, which is what I have here below. This is dA, 1/2 of r squared d theta. Okay. All right. 2/3 r cosine theta, 1/2. Everybody following? So if we take the summation or the integral of that x dA from the first triangle that you find here at the beginning, this will be the first triangle here. And then you add all the triangles that you find, another one here, another one here, another one here, another one here. Is infinite number of the triangles. These are triangles that are very little. I am drawing them really big. They are infinitely small. If you take the center of gravity or the first moment of those little areas, all those, and divide by the total area, we will find x bar. So let's do it. So we have to do all those areas from the when the angle is here at the floor following the x-axis, that's when theta is equal to 0, and then we sweep the whole area all the way up to theta equals to pi over 2. So we have to do the integral. X bar will be the integral of x dA from 0 to pi over 2 over the total area, right? So let's do the numerator. The numerator will be integral from 0 to pi over 2 of x dA, that we have it here. So that will be 2/3 r cubed or 1/2 cosine theta d theta. I guess we can get rid of this, and we have 1/3 r cubed integral of from 0 to pi over 2. We got the 3, we got the r cubed, so cosine theta d theta. So this is equal to 1/3 r cubed. The integral of cosine is sine, right, guys? I remember that the derivative of sine is cosine, so the inverse is the integral of sine theta from 0 to pi over 2. So let's continue here. I have 1/3 r cubed, and I have sine of pi over 2 minus sine of 0. So that will be 1/3 r cubed. Sine of pi over 2 is 1 minus 0. So this is equal to 1/3 r cubed. So now we need, this is the numerator of this expression here. So x bar will be this 1/3 r cubed over the area. The area is 1/4 of pi r squared. So this comes to be 4/3 r over pi. All right, that's another figure, another basic figure that we have the location of the center of gravity that we will be able to use in any of our problems to follow. So now we know that whenever you have a quarter of a circle like here, being the radius r, the center of gravity is located at a distance equal to 4/3 r over pi. All right. Okay. Well, that's another figure that we have. So what do we have so far? We have that we know the location of the center of gravity of a rectangle, which is just in the middle. If this is A and this is B, the center of gravity is A/2 or B/2. We know also the triangle. Basically any triangle. We did like 3 triangles. If this is B and this is H, the center of gravity will be over here somewhere where this distance is h/3 or this distance is b/3, or if you have it like this, well, and also, well, this distance is 2h/3, right? And this distance will be 2b/3. And if you have it like this, we could, if this is B and this is H, then the center of gravity will be somewhere over here. Someplace over here where this is h/3 and this is 2h/3. Oh, with the one that we did last time, it was like an isosceles triangle, the same isosceles triangle like this. Then this distance will be b/2. So basic figures that we have already, and in order to do more complex figures based on this. With common sense, we see that the center of gravity of this circle is right in the middle, right? I don't think we need to do any demonstration of that. Okay, I think that will be enough for center of gravity. I think I can give any more chalk to this topic.